Okay. Let's wait for people. Can you guys hear me? Nice. Let's wait for the others. We are 13 now. Let's see. Fourteen. Okay, the others will reach us, I guess. So guys, today we are going to speak about EKF SLAM with unknown data association. So we will use the same building blocks of the last exercise when we speak about EKF SLAM. In this case, we don't know the IDs of the landmark, which was that number that allowed us to identify to which point which measurement belongs. So the outline, we will describe the scenario again. So we include the definition of the state, the controls, the observations, transition function, observation functions, and blah blah. And we will adjust this new piece, so the data association part. All of this will be identical to the EKF SLAM exercise, okay? So we will recap it really quickly. So the scenario, we have still the Orazio moving in 2D, is controlled by the usual controls, so translational velocity, rotational velocity, and blah blah. We have a 2D landmark sensor, but in this case, we don't have the prior knowledge of the map, as in SLAM, but we don't know what we are observing in which point in time. By what we observe, I mean the ID of the specific landmark that I'm seeing in this particular position, okay? So approaching the problem, same as before. So I hope this part is should be clear by now. So we define all the usual quantities. Pay attention that even in this case, we don't have the prior knowledge of the map. So that's the usual EKF, which is written wrong. Sorry for that. So that's the usual recipe. So we will do the prediction step. Given the transition function, we compute these two Jacobians. So the Jacobian of the transition with respect to the state and the Jacobian of the transition with respect to the control. And then we project the previous covariance of the state, and we include also the uncertainty about the controls. Then we have the correction step. So this is our observation function. We derive it with respect to the state to obtain this Jacobian over here. And then we apply the recipe for the Kalman correction. Also, we have to take into consideration that while we are seeing the map, so while we are seeing the environment, we have to extend our state to include those landmarks inside the estimation process. Okay? Nothing new so far. The usual domains, so the pose of the robot is defined on a manifold, but we parameterize it as a Euclidean vector in 3D. As always, the landmarks are 2D position in the space, 2D controls, so this is the translational velocity, this is the rotational velocity, and we observe a 2D landmark, so x and y coordinate, okay? So we're not working with bearings. Transition function. Again, Same as before. So that's the kinematic model of the unicycle after Euler integration, so first order integration. So this is how the state evolves thanks to the controls. The landmarks are not actuated, so they will stay the same. Measurement function, usual thing. So we have to, given a landmark in our state, which is defined in the word frame, we have to transform it in the robot frame, and that's the predicted observation about that landmark. Okay. Control noise, same as the last time. So a constant part and a part which goes like the square of the velocity that we apply to the motors, that the motors actuate. Sorry. Measurement noise, we take always the constant. I know that is super boring, but if you have any question on all of these parts, just write it in the chat so that we will remove the doubts immediately. Transition Jacobian dimensions, I hope they are clear by now. So the Jacobian of A will be dimension of the output of the transition function, so the state, dimension of the state. In this case, 3 plus 2 number of landmarks, and the same apply for the columns. So the A is always dimension of the state times dimension of the states. We already see those blocks in the previous lectures, so this is the one that we see also in localization, and this is basically a gigantic column of zeros, and then you have an identity in the position that corresponds to the specific landmark. The B, it's even easier because we have just this part and the landmarks are not actuated, so it's a gigantic column of zeros. Jacobian of the measurement, we see it last time, is like a sparse Jacobian, let's say. So we have just 2 blocks which are non-zero, so the block that corresponds to the position of the robot, as always, and the block that corresponds to the landmark that we are observing in that specific time instant. Okay? So if I observe a landmark I from the robot position, I will have in indices that correspond to I a block which is equivalent to the transpose of the rotation matrix that we have here. So RT, where T I mean transpose. Now let's come to the new part. So in this specific exercise, we don't observe the landmark IDs, which means that every time I get an observation, I don't know if what I observe is something new, is something that I already have in my state, okay? And I don't know even the identity of the landmark that I'm observing, okay? So for convenience, as we did in the last exercise, we define these 2 mappings, ID to state map and state to ID. And as you remember, this basically was an association that tells us, okay, the landmark with ID 5 is in the position 3 inside my state, because my state is represented as a gigantic vector. So every time I was getting an observation with a specific ID, I have to know in which position of the state vector that landmark is. And that was pretty easy because we know the IDs. So it was enough to define those mappings, and in the position that here that correspond to the ID of the measurement, I will put the index of the state vector that I need. And here will be the opposite mapping. So given the ID, the index in the state vector, I can get the ID of the landmark. Okay, this was a convenience because we were extending the state while we observe stuff. Okay. Now the problem will be that we don't have access to this ID directly. Okay, so we will always use those mappings because it's an easy management of our state vector and observation. But we have also to identify the landmark, so that once we identify it, we can infer the ID and then get the corresponding index inside the state vector. Is this problem enough clear, guys? I'm a little down with the question. Wait, I will put myself live. Is that clear, this part about data association? Like, what's the problem in this point now? More or less. Someone. Okay, I assume it's clear. Okay. So let's go by steps. Okay, imagine that at the current time step, which we define by t, we observe 3 landmarks. So we never observed something before. So what we will do is that we just add those landmarks inside our state. And we will give them an ID. ID1, ID2, ID3. So that's not a big deal. We have nothing in our state as landmarks, so we have no knowledge about the map. So every time, the first time that we observe something, we just add it in the state. That's the easiest thing to do. Okay? Now, what happened when I reobserve something? Like in this case, I'm observing this landmark, this landmark. The problem that we are going to solve is basically to identify whatever these 2 measurements belong to these landmarks. Or, for instance, in this case it seems pretty obvious that these are the same because they almost are in the same position. So these little offsets between the observation can be due to noise. Okay. While in this case the distance is a little bit bigger, so actually here we have to properly determine if this measurement associated with this guy, so I observe the same thing, or this thing is a new guy, and in case I have to assign to him a specific ID. Okay, how we will do that? So how we can distinguish between something that we see for the first time and something that we already observe, and further identify the corresponding landmark. Like if I understand that this I already see it before, I have also to infer to which landmark these measurements belong. So what I'm actually reobserving specifically. Okay. So as the professor tells you in the lecture of Friday, to solve this problem, we have basically the easiest, is not the most efficient way, of course, but the easiest from a theoretical standpoint approach will be to compute the likelihood of the associations. Okay, so we take all the measurements, all the landmarks that we have in our state, and we construct a gigantic const matrix, and then we try to find, by exploiting rows and columns, the association that minimize the overall cost. Okay, so first, how we can compute the cost of associating a specific landmark, let's say landmark n, with the observation m. Okay, so we take our prediction function, observation function, sorry, okay, which give us the predicted landmark, minus the measurement, both of them are 2D vectors, and then here what I'm doing is basically I'm computing the Malanobbius distance between prediction and measurement. Okay, this is actually an inverse covariance, so this is fully a Malanobbius distance. So it's a distance that takes into consideration the uncertainty about my measurement, let's say. Okay, so the computation of this guy can be made as follows. Of course, as I said, that's just an inverse covariance, but what I have to do, that's my covariance related to my state. Okay, and then I have the observation function that we can see as a mapping from the state space to the measurement space, right? Now, if I want to project this covariance to the measurement space, because of course this guy have dimension 2 by 2, so the covariance is related to the measurement. So what I have to do, and instead this is a gigantic guy which is tall and large as much as my state. So I have dimension 3 plus 2 number of landmarks, okay? And I have to project it to a 2D object to compute this Malanobbius distance. So what I will do, I cannot project directly a covariance inside a nonlinear function. So I will do the usual trick, I will linearize. So I will compute the Jacobian of this guy, C, and then I will do first order error propagation. That is exactly what we do in the prediction step of Kalman, right? Like we linearize the prediction function over the state, we take the previous covariance and then we multiply by the Jacobian of the transition and the Jacobian transpose. Okay? Here we are doing the same in the observation space, let's say, to make this uncertainty consistent with the measurement. Okay? And here we add some constant just to make then the inverse more stable, let's say, okay? Or to take into account the fact that due to the linearization, of course, we are losing something, okay? As the professor was explaining to you, I think 20 minutes ago, something like that, we could do the exact same thing using the ascendant transform, which will be, let's say, a more accurate approximation of this covariance, okay? But for simplicity, we will stick with the Jacobians up to now, okay? So for each association, so for each pair landmark measurement, what I have to do? I take the sigma of the state, which will be always the same, of course, and I will just compute the Jacobian that relates to my observation in this case, okay? Then I will perform the multiplication, getting this sigma, compute the inverse, and then compute the Mahalanobis distance, and fill it inside this gigantic cost function, okay? So, of course, that's an immensely expensive computation, because imagine that I have 5,000 landmarks and I don't know, 30 observation. Imagine the amount of computation that I have to do. Also because for each entry I have to invert a matrix, which can be expensive when you do it 20,000 times, even if the matrix is small, okay? Then, once we define this cost function, we have to find a way to minimize the overall cost. Do it in closed form is an NP-hard problem, so we have to go through heuristics. So, and the first heuristic, which is really simple, is just for saying, okay, I will accept an association just if the cost, so the specific entry of this matrix, is below a certain threshold, okay? That's really easy. So what I will do, I will take each of those rows, and these rows represent the measurements, okay? This is capital M is the measurement, capital N is the landmarks in our state. So for each measurement, I will extract the minimum over the row. So I will take the landmark that minimizes the cost for that measurement, okay? Once I select that, I will say, okay, if the cost is below the threshold, I will accept it. So that association is good because the Mahalanobis distance is small, basically, okay? While if it exceeds the threshold, I will just throw it away, which means that I will not associate this specific measurement with any landmark. So that measurement will not contribute in the correction step of our filter, okay? And the reason is, if you misassociate something, you will basically destroy the estimate, okay? And this we will see it later. So that's the first heuristic, really, really simple. In this way, basically what we take for each measurement, we associate a single landmark, and we try to take all good landmarks, let's say, all landmarks which are close to the measurement in the Mahalanobis distance sense, okay? Then the second heuristic, which is the best friend. So that's another level, let's say, of security to guarantee that we have all good points associated. In this case, we don't only says, okay, take the best over the rows, right? So for each measurement, take the best landmark. But in this case, we also say, okay, for each landmark, take the best measurement. Now, if the two minimum, like let's consider this case. So for this measurement, I will take the minimum over here. Let's say that this minimum is A23, right? And this comes from the gating, okay? Now, I will take the minimum over the column of this guy. And if it happened that the minimum over the column for this specific landmark is A13, I will discard the association. So I want to be sure that not only I associate the landmark which is the closest to the measurement, but I also want the measurement which is the closest to the landmark. Because sometimes these two things, of course, don't coincide, okay? So I will take the minimum in both sense. If those are equal, then I will take the association, otherwise I will throw it away. Also, this will not contribute to the correction step. Now there is a third level, even, where we say, okay, we take the minimum over the rows and the columns. So the closest association in Mahalanobis distance both sides, but also we want to be sure that this is the absolute best association that we can get. So what we do, not only we take the minimum over rows and columns, but we take the second minimum, let's say, okay? The second minimum cost for both the rows and the columns, and we want to guarantee that the distance between the first and the second is pretty high. So it means that the difference between, I don't know, this guy and this guy, let's do it for a row, just for simplicity. So I want that these two things, this is the minimum, this is the second minimum. I want that these two things are as far as possible, which tells me that there is no doubt that this guy is the real association, because if these two things are closed, this difference can be due to anything. It can be due to noise, can be due to the linearization that we are performing to compute the covariance matrix. It can do to any effect. So actually the association is ambiguous because I have two entries that are really close to each other. Okay, so to avoid that, I have to introduce this third heuristic that says, okay, I will take the minimum and the second minimum, and I want to have something which is above this threshold. So if it's below this threshold, I will discard it. And I will repeat the same for the column. So if it passes all these levels, so gating best friend, which means minimum rows and columns, and lonely best friend, then this association is a good association, and I will use it inside the correction step. So as you see, data association is pretty tough. It's not tough to implement, but it's so important that we have to put a lot of levels of security, because otherwise our robot will get lost and bad things can happen. I think we will see it moreover in the course, because we will speak again, of course, about data association in the future. So now the hands-on program, but first I want to know if there are any questions, because I know that this part is a little bit tough, both the theory and the practice. At least it was tough when I followed the course some years ago now. So if there are any questions, like bring it out right now, so that then we can pass to the practical, where we, of course, we will not re-implement all the SLAM stack. We will just implement the data association part. Okay, there is something which is unclear, tell me. Okay, I don't see anything. The part of gating, sure. So, it's not clear why, I guess. Okay, then I will repeat also to Mariam. Wait, Giorgio, I will explain it live. It's, yeah, I have the slide here in front of me, instead of you writing 300 words, I guess. Then if you want to add something, of course, fine. So, for the gating part, what are we saying here is that, okay, here I have all my measurements, and here I have all my landmarks, okay? So, the data association problem, we want to associate to each measurement a specific landmark, right? Because a measurement cannot be associated to 3 landmarks at the same time. I'm observing one landmark, okay, when I consider a single measurement, okay? So to do so, we have this measurement and we want a single landmark, right? So these are the costs of associating this measurement to each of those landmarks. And as we said before, that's the Mahalanobis distance, right? So to take the best, because we want to minimize the overall cost, okay, of this association, so the overall Mahalanobis distance, in a way, what we do, we can take just the minimum over here, right? We take the minimum and we say, okay, this entry for this measurement, this landmark for this measurement is the one that minimizes the cost individually, for an individual measurement, right? That's pretty easy. Now, what we want to say is that we want to accept a measurement just if it have a minimum Malanobis distance, like it might happen, for saying, now we'll speak in meters, okay, just to make you clear. Instead of the Malanobis distance, I will speak like it's a normal distance, right? Now if I select this row and then I say, okay, this is the minimum, but then I discover that the actual distance between the landmark and the measurement is 10,000 meters, right? So geometrically, these two things are completely far apart. They belong to two completely different parts of the environment, okay? But if I use just the minimum over the rows, that's the association that I'm going to take. And you can imagine that if I have this sort of outlier, all my estimate will move towards this error and will corrupt my estimate, right? I hope that's intuitive. If it's not, tell me. So to avoid this case, what I can do, I can say, okay, I will take the minimum over the row, but I want this distance to be not so big, right? I assume that if a measurement belongs to a landmark, the distance between these two should be small, right? I'm saying a number just for speaking, centimeter level, not kilometers level. So to incorporate this kind of reasoning inside the heuristics, we can use gating. And we say, okay, I will take the minimum, but I will accept it just if this Malanobis distance is below a certain threshold, let's say 5 centimeters, I don't know, whatever. Okay, so that's the meaning of gating. Avoid to have association which in fact represent measurement and landmarks that are really far from each other. Is that clear now, Marco? Then I will switch to Mariam. Marco, I have always like 30 minutes of delay. Nice. So Mariam, since we know that lonely best friend is the best heuristic to use out of the three types, then why do we still have to use gating and best friend? Actually, you don't use just one of these. You use this in cascade, right? If you think about. So this is not that I will use gating, or I will use best friends, or I will use lonely best friends, right? I want to have the maximum level of security. As I was telling before, if I have an association which is corrupted, let's say, so I'm associating a wrong measurement to or the wrong landmark, whatever, all my estimate will move towards that error. This is a known effect, let's say, when you work with Gaussians, so mean, covariance, and whatever. So what I'm actually doing is that first I perform gating, so I will filter out part of the broken association. Then I will perform best friend, and then I will perform lonely best friend. In fact, if you see here, lonely best friend just compare the best by row, the best by column with the second best both sides. So it's actually implicit that first I have to perform the best friend, right? Because I want these two guys to be the same association. So you perform it one after the other to be as sure as possible about what you are associating in your filter, okay? Is that clear now, Mariam? Always 35 minutes of delay. Mariam. Okay, nice. So if there are no other questions, I will say that Giorgio will send the link for the Google Meet so that we can start to dig into it. Of course, if you have last minute question, write it like now. Giorgio, you will send the link or I will send it? Okay, that's close. Okay guys, so we will send the link through the mailing list, so see you there.